MD. I'd be happy to answer them after class. Okay, so let's first just talk about what's left in the semester. So first, there's a quiz today, the last quiz. There's no lab this week. But then next week, we're just going to do the post-test of that intuition test. So that's only half an hour long. So lab will be super short next week. We're just skipping the third lab exam, and if you take this test, you get 100 on the third lab exam. So now you might ask, what if I don't take this intuition post-test? Then what do I get on the lab exam? And I don't know, I hadn't really thought that one out. Seems kind of harsh to give you a 0, but I don't know. But if you take it, you get 100% on lab exam 3. And then the last thing is the final, exam 5. There are 2 times you can take that. Monday, 12, 11 at 6 p.m. in this room, 1326. Or if it works better for you, you can also take it Thursday, 12/14 at 2 p.m. One room over this direction. That's S1328. So if you can make it to both of these 2 times, you can just choose whichever one. If if you want to get done early and you're ready for it, you can take it Monday and be done. If you need a couple extra days to study, you can take it Thursday. And then that's all. And remember this exam 5. So exam 5 counts as itself in the grades no matter what. But if you have any of your first 4 exams that are lower than your score on exam 5, then your score on this will count as exam 5 and it'll replace your lower score. So if you have any zeros or anything, this is a way you can make up for your 0. Or if you have any just low scores, this can bump your grade up quite a bit. Anybody have any questions about the final stuff in this class? Yeah. Right, it's just the same length as the other tests. So I think we're scheduled for like 3 hours or something, but please don't stay for 3 hours. Yes? I don't know. I don't remember. All I can say is exam 3 is graded for almost everybody, not everybody. Exam 4, I think I haven't started that one yet, but I think at this point in the semester, I'm just like, I have a big pile. The pile keeps getting bigger. I just keep trying to work through the pile. I can't make any more promises about when stuff's going to be done. Any other questions? Okay. We're going to skip one topic and move on to the next one. We're skipping topic called conservation of linear momentum. Excuse me. That's going to come back. Okay, so we're skipping conservation of linear momentum. That's useful in collision problems. And we're skipping ahead just so we can get to two things that are more important, I think, than this. We're going right to conservation of mechanical energy. So first, we have to know what conservation means. You know, both of these have conservation in the title. In science, conservation means things stay exactly the same. So conservation of linear momentum or conservation of energy mean that at any time the linear momentum or the energy is exactly the same. That's a little different than the way we use conservation in everyday language, you know, like we talk about like nature conservationists going out and planting 1,000 trees or something. That's sort of a different usage, you know. If you were a real nature conservationist, you would sit there with one tree just waiting for another tree to fall down, and then you'd quickly plant it, and then you'd wait for the next one, you know. Conservation means that things stay exactly the same. So we're going to be talking about conservation of energy, and there's one thing that we have to get sort of clear about this. So conservation of energy. There's sort of two meanings for this that are relevant. The first one is that in the universe, let's say if you add up all the energy that stays constant. And that's a fact. Energy transfers from one type of energy to another type of energy. You know, sometimes that energy is stored up in things moving quickly. Then sometimes that energy is light or the creation of sound waves. There's all these ways energy can be represented. But if you find all that energy in the universe and add it all up, it's the same as it was 100 million years ago, and it's the same as it will be in 100 million years. If you add up, yes, all the energy, that stays constant. This is true, but it's not exactly what we're going to be, it's not exactly the thing that we're going to be using in this class. So I want to make this distinction. This is true always. There are never any cases where it's not true. This isn't really what we're talking about in this class. Then the second meaning is under certain conditions. So this is not always true. If you add up the mechanical energy of a collection of objects, that stays the same over time. That stays constant over time. This is not always true. This is the one that's relevant in this class, the one we're using in this class. So why wouldn't we use the general one that's always true? Well, calculating the total energy, if you're dealing with every possible way that energy can be presented, is a really hard thing to do. On the other hand, calculating the mechanical energy of one object or a couple of objects is relatively easy to do. And so we're just going to focus on the cases where, and we'll have to define what mechanical energy is. It's going to be made up of two things, kinetic energy and potential energy. But those are going to be pretty easy to calculate. And under certain conditions, we can use this law of conservation of mechanical energy to figure out the speed things are going, the height things get to, that kind of stuff. Okay, so this is the one that matters to us. And the general idea of conservation of energy, that's one of the very important ideas in all of science. But that's not exactly what we're doing, although these two are somewhat related. But one is always true, but hard to calculate. One is easier to calculate, but you have to be really careful about when you apply it. Okay, the conservation of mechanical energy is a special case of what's called the work energy principle. And so my approach is I'm going to talk about the work energy principle, define the terms, and then little by little we're going to work our way from the general work energy principle, which is not always true, but it's true more often than the conservation of mechanical energy. And we're going to finally end up in this equation, conservation of mechanical energy. And hopefully, as we go through that process, I'll sort of give you a good sense of when you can use that conservation of mechanical energy and when it doesn't apply. Okay, that's going to be the path I'm going to follow. So here's the work energy principle. It says that if you take the work done by each individual force acting on a body and add them up, that's equal to change in kinetic energy. So this is the law. The work total is the sum of the works done on the chosen body by all the individual forces acting on that body. And this capital delta KE is the change in kinetic energy of the chosen body. Okay, so for the first, I don't know, while for one class or something, our focus is going to be on this equation. Eventually, under certain conditions, this equation is going to simplify to the conservation of mechanical energy. And so before we can use this, before we can use the work energy principle, we have to define work and kinetic energy. So I'll talk about how to calculate each of these individual things, and then we'll talk about using this equation in pieces. So first I'll talk about work. So in words, you can think of work as being the energy added to a chosen object by the application of a force. This is as opposed to, you can also change the energy, add energy to an object by putting it next to something with a different temperature. So anybody know what it's called if you add energy to an object with a difference of temperatures? That's called heat. And we tend to, in everyday speech, we tend to use the word heat as meaning like a high temperature, but heat is actually not a temperature. Heat is energy transfer from one thing to another because those two things have different temperatures. So, yeah, as opposed to heat. Yeah, I don't know about hot. I think hot maybe just does mean high temperature. That's not something you use in science, uh, but yeah, heat technically is just energy that's transferred from one thing to another because there's a difference in temperatures. And those different ways uh, of transferring energy can be, sort of interchanged. You can, through the application of a force, you can change the temperature of something. Like, for example, if you had a insulated container of water and you had a little paddle wheel that you got spinning really fast, it would raise the temperature of the water, even though you're transferring that energy in by applying forces. And you can also, I mean, this is how like any kind of steam engine or even combustion engines work. Like if you have a gas inside a piston and you increase the temperature of the gas by, so that's energy transfer through heat because you're using a temperature difference. That increased temperature of the gas makes the gas expand, which pushes up the piston and applies forces to other objects. So you can go back and forth with these. But the one that we care about is work, and that's just energy transfer due to applying forces. Yep. Nope. So it's the energy transfer is work because you're just applying forces, and because of that, you have an increase in thermal energy in the liquid. Yeah. Uh, okay. So um, the way that you calculate the work is as an object moves from point P1 to P2, the displacement d, and remember displacement's a vector, is just the coordinates of P2, so I'm going to write that as a vector, minus the coordinates of P1. We've done some of this kind of stuff in 2D kinematics. Then the work done by the force vector F as the object travels from P1 to P2 is work is equal to the force vector, and then this is a new operation for vectors called the dot product. So you just write a dot like the way, if you did that with just numbers, it would just mean you're multiplying them together. But F dot D, where this dot is called the dot product, and the way that operation works is you multiply the two x components of these vectors together. So the x component of F times the x component of D, and then add that to the product of the two y components. So that's the definition of the work. For example, if you're taking the dot product of, 3, -4, and 8, 6, The way you calculate that is 3 times 8 plus negative 4 times 6. And that's 0. 24 minus 24. I'm not going to go through like mathematically why this works, but here is sort of like the intuitive way to think about how the dot product works. So the intuitive meaning of the dot product first, if F and D are within 90 degrees of each other, we're just talking about their directions, and the work is positive, and that means that the force is adding energy to the object. Second, if F and D are over 90 degrees apart from each other, then the work is negative, and the force is removing energy from the object. And then the last possibility is that they're exactly 90 degrees apart. So if F and D are exactly 90 degrees apart, the work is 0. And that means that the force isn't changing the energy of the object at all. Okay, so this example we did here of showing just how to use the dot product, I just randomly picked these numbers, but when you take a dot product of these two, you get 0. So what's the angle between those two vectors? 90 degrees. Let's do a couple other examples so you sort of see what this looks like. So what would be the dot product between a vector, that vector there, and that vector there? Do those look like more or less than 90 degrees apart from each other? Less, you have one going that way, one going that way. This is less than 90 degrees. So this is going to give you something positive. What about this? And you take a dot product with this. So that's a vector this way and a vector this way. Is that more or less than 90 degrees? Yep, this is greater than 90 degrees. And so this is going to be negative. And then if you have two that are exactly 90 degrees apart, you have one like that, one like that. This is 90 degrees, and so that dot product is equal to 0. Notice that even though you take a dot product of two vectors, the answer is just a number. You don't get a vector for the answer. So the answer is a scalar, a number. So in other words, work doesn't have direction. And that's not only true of work, that's true of anything related to energy. Energy never has a direction. You either have a lot of it or a little of it. You can make it go up or down, but you increase or decrease, but you can't change the direction. There's no such thing as direction. So that's true of any type of energy. Oh, I know what else I was going to say. So let's say this is the thing to notice, number one. Okay. And then the second thing I want you to keep in mind is that when we're talking about something increasing or decreasing energy, for now, I just want you to notice that energy is related to speed. So if you make something speed up, you're increasing its energy. If you make something slow down, you're decreasing its energy. And that's the way to think about what this work is doing. And there's one more thing. I definitely wanted to say this too. Okay, so speeding up is increasing energy, slowing down is decreasing energy. And last thing is, based on this definition of work, what would you get for a dot product between, say you had some big force, 1,000,000 newtons for X and 1,000,000 newtons for Y, and you took a dot product of that with the zero vector, 0, 0. What would you get for a dot product? Yeah, 0. So you can't ever have work if without the thing moving. Okay. So a force can only do work to an object that's moving. So if you're doing like isometric exercises or whatever, you're pushing against a wall or a railing as hard as you can, like it's hard work, you'll be sweating and whatever, and inside your cells will be doing work and stuff. But if you're calculating the work that you're doing to the wall or the work that the wall's doing to you, it's going to be 0 because you're still. Okay. Anybody have any questions about this yet? All right. So let's do some sort of intuitive examples. And here's what I want to imagine. Let's imagine that we have this thing rolling along train tracks. Okay, so you have this cart that's rolling along train tracks this way. And so this cart can't move side to side. All it can do is move along the tracks. And so first, let's think of it in a top view. So here's the cart, and it's starting at P1 and ending at P2. And so here are the tracks. And the thing, it's going this way. Let's say that the force applied so say you apply a force this way, which, along the direction of motion. Okay, so is the work done on the cart by F positive, negative, or 0? All right, well, the first thing we have to do is figure out what the direction of the displacement is. The displacement vector just goes from the starting point to the ending point. So that's the displacement vector. And so if the displacement vector is this way, and the force vector is in the same direction, are those more, less, or equal to 90 degrees apart? Yep. 0 degrees apart. So the work is positive. And if the work is positive, is this force increasing or decreasing the cart's energy? Any other guesses? Come on. Increase. Didn't you say decreasing before? Oh, you were right before then. Increasing. So if positive, the thing's energy is increasing. So the force is increasing the cart's energy. Now let's think about it in terms of, so remember I said that energy is related to speeding up or slowing down. So let's think about it in those terms. If this thing is going from P1 to P2, then its velocity direction is that way, right? And so imagine this thing that's moving that way. This thing's sliding, rolling along these tracks, and you get behind it and push it in the direction it's going. Is that going to slow the thing down or speed it up? It's going to speed it up. And so it makes sense that if you think of energy as related to speed, it makes sense that a force in that direction is going to increase the energy. Okay, so it makes mathematical sense if you think about this dot product thing, and it makes physical sense if you think about whether that force is going to speed it up, slow it down, or have no effect on its speed. Okay, so now let's say example 2. It's still starting at P1 and finishing at P2. And it's still going along these tracks. But now the force is this way. And we want to know, is the work positive, negative, or zero? Well, the displacement vector is still, it's just a vector from the starting point to the ending point. So that's the displacement vector. Now the force is in the opposite direction. So we have a displacement like this, a force vector like that. Are those more than, less than, or equal to 90 degrees apart? Yep. This is over 90 degrees apart. And so in this case, the work is negative. And if the work is negative, is the object speeding up or slowing down? Slowing down, yep. The cart is, or you could say, actually, let me reword this. Let me say the force F is removing energy from the cart. And that relates to speed because, if something's energy is being reduced, speed is being reduced. So let's think about it intuitively. So again, if the thing is moving from here to here, its velocity is that way. Okay? And now imagine that you apply a force that way to it by getting in front of it and pushing against it. So now you're on this side pushing back as it moves this way. And so the way that would work is like maybe at the time it's at P1, it's already going really fast because of stuff that happened before. And now you start applying this force to it, but it still is moving fast enough at the start that it still makes it here. You know, you can't apply enough force to stop it. But the force that you apply to it, is it going to speed it up or slow it down? Like you're fighting that velocity.
Slow it down.
So yeah, you're going to slow it down, and that matches the mathematical idea that the energy is being decreased. Anyone have any questions about that? Okay, so then the last example. So it's the same setup. The cart's going this way from P1 to P2. And it's on these train tracks still. And this time, a force is applied this way. So what's going to happen here? The displacement vector goes from the start to the end. So that's the displacement vector. If you compare these two angles, you have a displacement this way and a force this way. The angle between them is 90 degrees now. And so the work this time is 0. And this is a little trickier to imagine. Well, so let's think about it in terms of energy. If the work is 0, then the energy is staying constant. So energy doesn't change, isn't changed by the force. So to imagine this, you have to imagine that this cart moves along these tracks without any friction. And you have to imagine that you're sort of running beside it, pushing it, you know, trying to push it off the tracks. Okay. Well, if the cart's moving this way and the force you're applying is this way, you're not going to have any effect on the speed. In real life, you would have an effect on the speed because that would increase the normal force, which would increase the friction or whatever. But we're going to imagine that there's no friction. And so applying a force this way doesn't have any effect on the speed this way. And so just like mathematically, we know that the energy isn't going to change from thinking about the work. If we think about it physically, we know that applying a force exactly perpendicular isn't going to have, it's not going to be pushing it to speed it up. It's not going to be pushing it to slow it down. It's going to have this unrelated effect on it. So that's sort of how this idea of speeding up and slowing down relates to the calculation of work. Anybody have any questions about any of those? Yep. Yeah, you're just trying to figure out sort of what's the difference in angles between them, you know? Like you could think about measuring the two of them with a protractor and then just subtracting to see the difference in angles. Okay. So that's work. And now we have to define kinetic energy. An object's kinetic energy, call it Ke, is equal to 1/2 times m times capital V squared, where m is the object's mass, and capital V is the object's speed. Okay, so things have more kinetic energy if they're bigger and faster. So a snail has very little kinetic energy, and a semi on the highway has a lot of kinetic energy. You have a question? Okay. Speed is the magnitude of the velocity vector. And so you can always calculate this. If you have the velocity vector, you can always calculate the speed by taking the x component squared plus the y component squared, and then take the square root. But actually, that brings up the next equation I wanted to put down. If what you know is the velocity vector instead of the speed, then you can calculate the kinetic energy as 1/2 times the mass times the x component of the velocity squared plus the y component of the velocity squared. So it's easy to calculate either way. And notice that, again, kinetic energy isn't a vector, it's a scalar. It's a kind of energy, so that has to be the case. Did someone have a question? Okay, so units for energy. Are you can think of it as force times length. And remember, force has units of mass times length divided by time squared. So you can also think of this as mass times length squared divided by time squared. And so SI units are SI units of force or newtons. Length is meters, so you can think of energy as having units of Newton meters, or you can think of it as having units of, using this other expression, kilograms times meters squared per second squared. Those are those are exactly the same units, just different ways of writing them. And since we use energy all the time, this sort of crazy looking set of units is given its own name. You abbreviate it with a capital J. Okay, so let's do an example. Yeah. So, like I was saying, there's all these different ways that energy can be, like energy can be expressed through light waves, and then you have to measure something about. I think in every case you kind of do measure the pieces that go into the energy, but how you measure energy just depends on how it's being expressed. You know, like you can measure energy by measuring the brightness of a light, or the loudness of a sound, or the speed and mass in this case. You know, so yeah, energy is kind of a tricky, like, yeah, it's not like you have an energy meter and you hold it up to something, and you know what I mean. That's right. Okay, so let's say that there is a guy on an elevator, and let's say his mass is 50 kilograms. And let's say that he has a scale under his feet, and the scale shows the floor of the elevator, applies an upward force of 490.5 newtons to the man. And we want to know first work on the man by gravity. Second, we want to know what's the work on the man by that force the elevator's applying. Those are the only two forces acting on him. So then we want to know what's the total work on the man. And then we'll use that to figure out what's the change in kinetic energy. And I actually, this doesn't mean anything until I say that there's some displacement this man goes through. So let's say this elevator rises 10 meters. Because if these forces are applied and that elevator just sits there, then the work is going to be zero. You need a displacement for the work to be non-zero. Okay, so if the elevator rises 10 meters, what's the displacement vector? Well, it's straight up 10 meters. If we call that the positive y direction, this displacement would be 0, positive 10. The force vector applied by gravity to the man is 0. 50 times 9.81 is negative 490.5. So the work done by gravity is 0 times 0, that's multiplying the x components together, plus 10 times negative 490.5, and that gives a work done by gravity of negative 490.5, nope, negative 4905 joules. So gravity is removing that much energy from the man. And now we'll think about the force that the scale or the floor of the elevator applies to the man. The displacement again is 0.10. But the force applied by the elevator is 0 positive 490.5. And so the work done by the elevator is 0 times 0 plus 10 times positive 490.5. And that gives positive 4905 joules. Any questions about that yet? And so now, we had a negative 4905 and a positive 4905, so the total work is 0. And so now if you look at the work energy principle, the work energy principle says the total work is equal to the change in kinetic energy. So the change in kinetic energy also has to be 0. Or the speed stays constant. And you could do the same analysis using Newton's second law like we've been doing up until now. And you would see that your answer said that with those forces, the acceleration is equal to 0. And constant speed and 0 acceleration are the same thing. So we used this energy idea to get a result that we could have gotten with Newton's second law. Okay, we'll keep going with this next time.